All right, so we just finished the front side of notes 12. We did not do the back side yet. All we've discussed are London dispersion forces and dipole forces. But I want to do half of the homework that relates to that portion. So homework 12 is intermolecular forces and their relationship to other properties. So the first one, what is the relationship between temperature and the phase of matter, intermolecular forces, and energy? Well, temperature and energy are not the same thing, but temperature is a measure of how much like heat energy is in the system. So those two are pretty easy to relate to one another. Phase of matter, that's referring to solid, liquid, or gas. And intermolecular forces are what we've been talking about. These are the sticky strings that are trying to hold molecules together, separate molecules together with sticky interactions. So if I have my IMFs, and these are, again, they're sticky, they're trying to hold together different molecules. Energy is the opposite. When energy goes into a molecule, it wiggles. It wiggle, 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 wiggle. And the more it wiggle, 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 the more it wiggles, the harder it is to stick together. It's not like the IMFs are changing. The IMFs are like a characteristic of the molecule. They are what they are, right? Every molecule has its own amount of sticky. If you have very low energy though, the sticky can stick together. But if the energy is high, then your sticky can't keep it together. So I honestly think of it like energy is kind of like stress. And if you have a lot of stress on the system and it's very, very stressful, then your coping mechanism of like how you hold yourself together, it is going to be harder and harder for you to hold yourself together the more stress is put on you. So the higher the energy, the harder it is for the IMFs to hold together. So when you have really, really high energy, you're more likely to be a gas because gases are all over the place. They're not very stuck together. The energy, when the energy is high, it's able to overcome the IMFs. That's how we get stuff like in the gas state. On the opposite side, if we have very low energy, like when it's cold, things usually will change into either a solid or liquid state. The lower the energy, the better the IMFs are able to hold it together. So generally when things are cold, they'll be solids, you heat them up and they become gases. So that's what I would write, something for number one. I think here's my my answer key. What is the relationship between blah, blah, blah? I'd say each substance has a certain amount of IMF sticky due to its shape or electronegativity, whatever. If IMFs are able to overpower energy, then it's a solid. But more temp, more energy, the more energy we have, we can overcome the IMFs and change it into states like gases. Explain the difference, number two, between a chemical bond and an intermolecular force. So for me, when we were a kid, I don't think you guys play this anymore. When I was a kid, we used to play a game called Red Rover. And everyone would line up in like a row. Okay, I gotta draw this faster. Like this. Okay, so everyone's holding hands, hand holding. There's a little hands, holding hands. Okay, so everyone's holding hands. And they say like, Red Rover, send Kaylee right over, whatever. And then my objective would be to run and try and pick like a weak spot. And I would try and break through to make these two people stop holding hands. They're holding hands, and then I'm trying to like get them to unlink. So holding hands is not a very strong connection. That's what I would say intermolecular forces are like. It's just an interaction between two people, two separate people interacting, holding hands. It's pretty weak. Now, if you were to actually compare that to a chemical bond would be like if you had to cut off someone's literal arm off of their body. That's the difference, because your arm is like bonded to you, whereas you holding hands with someone else is just an interaction. So it's much easier to overcome the interaction than it would be to sever your arm. So that's how I think about it. I wrote it a little bit more gracefully though in my answer key. I wrote, breaking a bond requires a large amount of energy. Bonded atoms are stable. IMFs are Coulombic attractions. Coulombic just means charge. So they're attractions based on charge, but no electrons are being shared like they would be in a covalent bond, nor transferred like they would be in an ionic bond. So electrons are still present. We still have arms. It's just, are they holding hands or are we cutting off arms? Bonds is like sewing. IMFs are like Velcro. That's what I wrote. The next one, what is the difference between a temporary and a permanent dipole? Well, a permanent, temporary versus permanent. You seem to know what those are pretty good. Electronegative atoms pull on the electrons. So in a permanent dipole, you're going to be working with polar molecules that always have one side that's partial positive and the other side that's partial negative. For example, hydrogen bonded to fluorine. Fluorine hogs the electrons. They go more towards him. So his side is always partial negative. In a temporary situation, the molecule itself isn't polar, like carbon, hydrogen, hydrogen, hydrogen. We don't consider carbon-hydrogen bonds to be polar. If you wanted like a perfectly non-polar example, you could do something like just a hydrogen bonded to a hydrogen. Those are going to share electrons perfectly. But the electrons are still moving. And if they accidentally both happen on the same side of your molecule, it will create a temporary imbalance. It'll like leave the next second, but for that one moment, there was an imbalance. So there's my example of each. And on my paper, I wrote temporary dipole equals London dispersion forces. Electrons are moving around. They might happen to all be on the same side momentarily. Permanent dipole equals dipole interactions. The molecule is polar due to the shape and electronegativity, which is permanent. The next one says, what is meant by the term polarizability? And I wrote, polarizability is electron sloshability, a measure of how easily the electron cloud can be distorted. That's the technical one, I guess I forgot to put in quotes. And it says, which of the following would be most polarizable? Oxygen, sulfur, selenium, or is that tellurium? So those on the periodic table are all in a column. Find oxygen, like legit find it. Look underneath it. Underneath oxygen is a sulfur. Underneath sulfur is a selenium. Underneath selenium is is it like tellurium? I don't even know. Te. So since Te is further down on the periodic table, it has more electrons. The more electrons you have, the more you're able to slosh them around.